In this video, we're solving an unusual calculus problem. So we're considering the parabola y equals 1 minus x squared, and that defines a region below the parabola but above the x-axis. And what we're trying to solve for this time is the value of a constant c, so that the horizontal line y equals c splits this area exactly in half. In other words, half the shaded area is above that horizontal line and half is below. And the strategy we're going to take here is to compute the total area under the parabola, and then we're going to compute the area in the upper half in terms of c, and then we'll set that area in the upper half equal to half the total. So the calculation for the total area is straightforward. This is just the area bounded under a curve, in other words, the integral on the interval of interest, that's -1 to 1, of the function that we're looking at, that's 1 minus x squared dx. And it's probably a good idea to take advantage of the symmetry of the function here. So we're just going to integrate the right half and then double the result. And that works because the entire area is symmetric about the y-axis. Now each of those pieces in the integrand is a simple power function. So when I integrate 1, I get x. When I integrate x squared, I get 1/3 x cubed. And we're evaluating that from 0 to 1. And the advantage of splitting the integration interval is that we have a 0 for one of our limits now. And when I sub that in for x, I get 0. So all I have to consider is my upper limit. So I end up with a 2 times 1 minus 1/3 when I replace x with 1. And 1 minus 1/3 is 2/3. And when I multiply that by 2, I get 4/3. So there's the area of the entire thing. So we'll go ahead and make a note of that down here. We have a total is equal to 4/3. And we'll go ahead and clear out some more space to work on the upper half. Now to find the area of the upper half in terms of c, the first thing I want to get done is to figure out the limits of integration, because we're no longer adding up area from -1 to 1. We're actually only integrating from this mark right here on the left to this mark right here on the right. And that's the point where the parabola 1 minus x squared intersects the line y equals c. So to do this calculation, we simply set the y values of these two curves equal to each other, and then we try to find out what x is equal to. So when I do that, I get 1 minus x squared is equal to c. And if I add the x squared to both sides and subtract the c, I get x squared is equal to 1 minus c. And then I take the square root. I have plus or minus the square root of 1 minus c. So the positive root there is going to be the upper limit of integration. The negative root is going to be the lower limit of integration. So we got those into the diagram. And now we'd like to set up an area integral for the area bounded in this upper part of the figure. And this is the area bounded between two functions. So we might want to actually visualize a thin vertical slice of this area like this. And we normally give that the expression dA, meaning it's an infinitesimal contribution to the total area. So I just need to get the height of that little rectangle and the width of it, and then we use an integral to add up all those little slices. Well, the height of it is just the difference between the upper and lower functions. So that's 1 minus x squared minus c. And then the width of that little slice is an infinitesimal little increment in x. So we call that dx. So now we can start working on the calculation of the area in the upper half of this figure. And we can say the total area is just the integral of the dAs. In other words, the sum of all those little dA contributions. And the dAs are found by just taking the height times the width for that skinny rectangle. So that's 1 minus x squared minus c times dx. And we're adding all these up from negative square root 1 minus c to positive square root 1 minus c. But I might as well right now use the same symmetry trick and just add up from 0 to the positive square root of 1 minus c. And then double the result because I have symmetry about the y-axis. Now when I get into this integral, it's advantageous to collect the constants separately from that quadratic term. So the constant there is 1 minus c, and then I have a minus x squared and dx. So the 1 minus c integrates to a 1 minus c times x. The x squared integrates to a 1/3 x cubed. And now we're really seeing an advantage to using symmetry here, because I don't have to put in a lower limit of negative square root 1 minus c. I just have a 0 there. And when I replace x with 0, again, the entire expression vanishes. So all I have to do is replace my x's with a square root of 1 minus c. Now in my first term, I'm going to end up with a 1 minus c times the square root of 1 minus c. And when I multiply those together, I get a 1 minus c to the 3/2. In my second term, I have a 1/3 square root 1 minus c to the 3rd power. That's also 1 minus c to the 3/2. And this is really important for our prospects of solving this problem. That 1 minus c to the 3/2 is going to factor out of the whole thing. And left over in the interior of these parentheses is a 1 minus 1/3, which again is 2/3. So this all reduces to 4/3 times the quantity 1 minus c to the 3/2. And we'll go ahead and make a note of that area under the diagram. So I'll call that A upper. All right, so finally we're able to execute our original strategy. I want to take the area in the upper half of the figure, and that's 4/3 times 1 minus c to the 3/2, and I want to set that equal to half the total area under this parabola. Well, the total area was 4/3, so half of that is 2/3. So immediately we can multiply both sides by 3, and we'll divide by 4. That gives us a 1/2 on the right side, so we have 1 minus c to the 3/2 is equal to 1/2. Then we can raise each side to the 2/3 power, and on the left-hand side we'll have 1 minus c, and then on the right-hand side we have a 1 over 2 to the 2/3. Finally, we can solve for c, so the way I would think about this is adding c to both sides and then subtracting the 1 over 2 to the 2/3 from both sides and then flipping the equation back around. So c is going to be 1 minus 1 over 2 to the 2/3. So that's one way of expressing the answer, but if we rationalize that denominator, I can do that by multiplying by 2 to the 1/3 on the top and bottom. In other words, the cubed root of 2. And I find that c is 1 minus the cubed root of 2 over 2. So that's a nice way to write the answer, but we might get a little more insight from a decimal approximation here. So when I get a decimal approximation, this is very close to 0.37. And this is good because we clearly needed a c value that was less than 1/2. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.